Okay, we are going to go through example 7.1 of chapter 7, the first example of chapter 7. This example is about a capacitor that is connected to a circuit. When the switch has been at position 1 for a long time and the capacitor has been charged to a certain amount, and we want to know what is going to happen when we are going from the switch is going from point 1 to point 2, and then we want to find the current that is flowing into this side of the branch, this branch of the circuit. Okay, before we start, we need to know before at time 0 and less, so what was the amount of voltage that was at the ends of this capacitor, how much was it charged for. So in order to find that, we have to consider a steady state condition in which we are going to have, so the capacitor is considered to be an open circuit, and so a 12 volt is connected to a 6K and then the 3K, and then we want to find what is the voltage across it. So in order to find the voltage, the only thing we need to do is this is a voltage division actually between the 6 and the 3. So I have a 12 volts, so the voltage over here, or the voltage over the V of the C at 0 minus, when I put 0 minus means anything less than 0, at 0 minus, or I call it V0, is going to be 12 volts times 3 over 3 plus 6. So that is the amount of voltage that appears over here. So this is equals to 3 times, so this is going to be 1 over 3, so this is going to be 4 volts. So the V0 before we start, actually before we go from this point to this point, is 4 volts. So we remember that. Okay, the second step is when we go from point 1 to point 2. Now this part of the circuit is out of circuit actually, and then all the voltage that has been, all the V0 that has been accumulated over here is going to go through this side of the circuit and that side of it, or to this branch and that branch, and we want to find this one. So before we find the I, we want to see how is the V changing, or we can how much is the V changing, but the change in the voltage is going to give us the current that is flowing in out of this branch. So if I write a KCL over here, then I have and if I write the KCL, I say the voltage that is provided by here, which is the current that is coming from here, which is C dV over dt, plus the current that is going over here, which is V over 3K, plus the current that is going over here, V over 6K, is equal to 0. I can write these VT because this V is changing by time. And then basically if I want to simplify this one, this is C dV over dt plus Vt, and then this 6K and R and 3K and 6K is actually the equivalent R, right? The R equivalent, or I just write it as R instead of R1 and R2. So this one was R2, this one was R1. So this is the R equivalent equals 0. One important thing that you need to know about these circuits is two important things that you need to know is what is the answer to a differential equation like this, and then the second thing, in order to find the answer, you need to know a constant which we call it relaxation time, which is equals to RC. So this R and this C, the RC. So the RC over here is now if I want to find the r, so 1 over 3, so 3 and the 6 so 3 parallel to 6 is going to be 3 times 6 over 3 plus 6, so this is going to be 2k, so my r is actually 2, and my c is 0. So it is 2k times 100 times 10 to the minus 6, so this is actually 0.2, so 0.2 in terms it is actually, because it is time, it is in seconds. Okay, the second thing that you need to know is what is the answer to the differential equation like this. So we covered that in class. We said that if I have any equation like so if I have an x of t, then the derivation of x of t over dt plus a x of t equals 0. The answer to this is x of t equals x0 e to the power minus a times t. Here a for us is the same as 1 over rc. It is equal to so the 1 over relaxation time actually. So the answer for our to our equation over here, so x for us is now v. So the answer to our equation, we know that a is actually so I write my dv over dt is equal to 1 over 0.2 vt equals 0 then this is equal to so I plus this is a plus equals 0, then I have vt is equal to v0 e to the power minus at, and a is 1 over c, so this is 1 over 0.2 and times t. And then if I want to finish this, I have to see what is v0 at time 0. So v0 at time 0, we found it to be 4 volts. So this is equal to 4 e to the power minus t over 0.2. I can write this as 4 e to the power minus 5t. So this is the same. This is the same, and my relationship over here, I could have also written that as dv over dt equals 5vt, so or plus this one equals 0. So these are all a variable of t. But if I want to find the current over here, we say the current, the I equals V over R, right? So our R is 3K. Our V, we found it to be 4 e to the power minus 5t. So, or e to the power minus t over 0.2. It doesn't matter which one you choose. So if I find, if I want to find V, I have 4 over 3k, right? So 4 over 3, I don't write the k, and I can write the everything is in milliampere at the end. 4 over 3 e to the power minus t over 0.2. This is in milliampere, so this is the current that is flowing over here.